Hello, my name is Chonghyun Won, graduate student in Yonsei University. And today we are going to present an optimization problem about the UAV enabled network and propose an efficient algorithm to serve it. First, let us introduce the motivation of the study. Recently, there are many studies on utilizing a UAV in a communication network because utilizing a UAV has many advantages in applying communication network, and also due to the limited resources of network, it is important to determine the optimal location of a UAV. However, in many recent studies, an omnidirectional antenna for transmitting is considered. But if we utilize a directional antenna for transmitting, we can save much energy. So we consider this philosophy in our study. So the contribution is it's okay. Is it not here? What is the problem? Thank you. Our contribution is we consider that UAV communication system with UAV which mounts a directional antenna, and we proposed a simple heuristic algorithm to optimize that system. Let us introduce the scenario of our system model. We consider a downlink communication system with one ground-based station and one UAV and N ground users. And the UAV plays a role as a relay, which receives data from the ground-based station and sends it to ground users. And we assume that the UAV has a rotating, so UAV can hover at a fixed location. Next, we denote the location of the ground-based station, the ground users, and the UAV like this. And we assume that the ground-based station and all ground users are located at ground level, and so their heights are 0, and the height of the UAV has a constraint like this. Next, we record the link between the ground-based station and the UAV as a backhaul link, and the link between the UAV and the ground user as an access link. And we denote the bandwidth for the backhaul link as B0, and that for the access link for ground user I as BI. And we also assume that there is no overlap between the backhaul link and the access link for the frequency bands. So there is no interference among all links. Next, we denote the transmit power of the ground-based station as P0, and transmit power of the UAV to ground user I is PI, as PI. Next, we present the antenna model of the system. The UAV is equipped with a directional antenna for transmitting, and the directional antenna has a controllable beam with omega radian. And we assume that the direction is fixed to be perpendicular to the ground. So this red arrow is the beam direction, and we use the antenna model with the antenna gain has this formula, and this means that the antenna gain is proportional to the square of the beam width if the ground users are located inside the beam, and if a ground user is located outside of the beam, the antenna gain is just 0. Also, we assume that the ground base station has a directional antenna for transmitting, and the UAV has a directional antenna for receiving, and they has a antenna gain like this. And for simplicity, we assume that all ground users are equipped with omnidirectional antennas for receiving. And our channel model, we assume that the UAV has a tour height enough for has LOS. So we adopt the LOS-based channel model, and accordingly, the data rate of the backhaul link is derived like this formula, and the data rate of the access link is derived as this formula. And here, these parameters represent this. And there are two constraints for about data rate. First is each ground user requires a minimum data rate, R min I. So each Ri should be greater than or equal to R min I. And the second constraint means the causality constraint. The sum of the data rate of the access link cannot exceed the data rate of the backhaul link. Based on the system model, we formulated the optimization problem, and the objective of our optimization problem is the weighted sum of transmit power of the UAV and of the ground base station and UAV. Here, W1 and W2 represent weight. And in our optimization problem, we control 3 variables: the location X of the UAV, the beam width omega, and P represents the power allocation vector. So all constraints were explained before. The first constraint means that all users require minimum data rate, and the second constraint means that the causality constraint, and the others represent the trivial boundary constraint. So to solve the optimization problem 1, we observed some observations, and we can derive the optimal P for given X and omega as a closed form, like equation 2 and 3. This is from the fact that because we should minimize the power, so the power of the UAV for each user should satisfy the equality of the constraint 1B, and similarly, the power of the ground base station should satisfy the equality of constraint 1C. So accordingly, we can derive these formulas, and also we can observe that the optimal beam width for a given location of the UAV is determined by the furthest user from the UAV. So we can formulate the optimal beam width omega star like this. And based on these formulas, we can reformulate our optimization problem as this. So the control variable remains only X, and we substitute P and omega as the optimal values, P star and omega star. So Although we reformulate the optimization problem, it is also not a convex optimization problem, but we can easily check that if we assume that this omega star is constant, this optimization problem is a convex optimization problem. So using this fact, we propose an algorithm to serve it. And we name the algorithm joint PBP, which represents algorithm for joint optimization of UAV placement, beam width, and power allocation. First, initialize the location of the UAV, and based on the location, we update the initial beam width, and we initialize the initial P0, initial P, and at each iteration, we update the location by serving problem 4, which is this, with assuming that this omega star has a constant value as the value of the previous step. And after updating the xn, we update the beam width omega. And finally, we update the optimal power according to this 2 and 3 formula. And we iterate these procedures until the objective value converges. And finally, we show that our algorithm, the performance of our algorithm with the simulation, we consider this simplest scenario for the simulation. First, the location of the GBS is just 0, 0, 0, and we place 8 ground users at the boundary of a circle, and the center of the circle is far from the GBS with 50 meters, and we change the radius of the circle from 0 to 100 meters. And as a comparison algorithm, we just optimize the placement and power, so the beam width is not controlled. And specifically, the transmitting antenna of the UAV is assumed to be omnidirectional. So we compare the joint PBP and joint PP to compare the effect of the directional antenna. And the result shows that joint PBP algorithm has much less, requires much less consumed power compared to joint PP algorithm. And as the radius of the circle increased, which means that the users become sparser, then the power increases because the optimal beam width also increases, and the average distance from the UAV and ground user increases. And also, we define power saving rate as this, which means that how much energy is saved when using joint PBP algorithm compared to when using joint PP algorithm. And we show that as the radius of the circle decreases, the power saving rate increases, which means that as ground users are denser, then the saving rate is efficient. So the summary is we consider the communication system with the directional antenna mounted UAV, and we utilize a directional antenna instead of an omnidirectional antenna to save the network resource. And we formulated the optimization problem and proposed the algorithm to jointly optimize the variables. And finally, we conclude that a directional antenna with controllable beamwidth can save significant amount of communication power. Yes, this is my presentation. Thank you for listening. And do you have any questions?
Thank you for presentation. Yeah, is there any questions?
I have a question.
Yeah.
Yeah.
Regarding the trajectory optimization, in your study, you just only optimize your height and Y axis. But my question is that why you don't optimize the height of UAV? Understand my question?
Oh, I'm sorry, I cannot understand.
According to your presentation, I see that
Here?
you just optimize height and Y axis of the UAV without considering the height of UAV. So my question is that why you didn't optimize the height of UAV?
So
This is height.
I also optimize the height of the UAV. Here, the control variable includes the X, and X represents the height of the UAV also.
Yeah. And another question is that you know that conventional algorithm, you know that you find the solution with considering the point channel gain, but you know that the channel gain is a change every time. Your algorithm maybe need many iterations to find the optimal solution, but at that time the channel gain is already changed. So maybe the change of channel maybe is the problem in your algorithm.
We just assume that the channel is not changed for the simplicity.
Yes, it is not very real implementation. Yeah, in the real time, maybe the channel is changed every change. So that's why it is the problem of the conventional algorithm.
That's all right. I cannot understand.
So he says,
Yeah.
in the air condition, the channel coefficient will be changing at any time.
Yeah.
But why do you consider that the channel is constant in your system model?
This is the system of snapshot. So we do not need to consider the change of the channel gain.
So is this answer will be answering to your question well? Maybe this is the area condition, but just in my opinion, the channel gain will be highly affected by the distance. So in his system, he didn't consider the small scale fading, and he only considered the large scale fading. So
Yes.
So in that assumption, in that case, this system model, this channel model is valid, I think. Is it helpful? Okay, thank you.
Thank you.
Yeah.
Okay.
Yeah.
In your scenario, you employ the user in circle. Is there any reason?
Well, I cannot hear.
In the simulation scenario,
Simulation.
yes,
Yeah.
you employ the user in the circle.
Yeah.
Is there any reason?
This is just to easily show the effect of when the user are dense and user are sparse. It's just simple scenario.
Because usually I see that they employ user in random location and increase the radius time.
Yeah, we also can simulate various scenarios, but in this presentation, we only show this scenario. Yeah. Thank you.
Okay, due to the time constraint. So yeah, thank you for presenting, Mr.